All right, so any questions so far? Did ODP 201 work out for everybody? Awesome. Okay. So that was kind of a how-to hello world for the one-day programs. I've posted ODP 202, which is due tomorrow morning at 8, and we'll talk about that in detail in a minute, but I want to go through the background of it first. So, show of hands, did you talk about the structure statement in 121? Okay, not necessarily remember it, but talked about it. So I want to start from there. I want to look at the struct statement in a bit of detail, and that will lead us into ODP 202 and also your first programming assignment. And after this, we're going to go back to looking at inserting things into a sorted array. But let's look at the struct statement first. So the idea of a struct statement is the following. Again, you have variables in a program. Those variables might be unrelated to each other, but there's a good chance that some of those variables have a relation to other variables. For example, you might have a student name and you might have a student ID, and that could be a string and an integer. And we'd like to somehow associate those together instead of every time we call a function passing a name and passing a string as two variables. So the idea of a C structure is to take multiple variables, possibly of different types, and combine them into a single entity. And so we can use the keyword struct, and we can create effectively a new type of variable. So I might say struct student, and then a curly brace as usual to start defining our structure. And now we just list all of the different variables that are a part of what we consider to be a student. So it could be a car star name, that's a string. It could be an integer student ID. It could be a double GPA. And it could be a lot more. It could be hundreds of fields. It could be things that are themselves arrays or structures or arrays of structures. So let's keep it simpler for now. So closing curly bracket and then a semicolon. And this statement can go in the beginning of your file outside of main, in which case everything from that point in your file on down has access to this structure. And it's usually where we put it, but more commonly we actually put this into a .h file and we include it. Because typically we're writing long programs, we're breaking them into different files. Every file is going to want to have this statement, so instead of typing this in 5 different places, put that into a .h file and just include it. But you can put it into each file, and it does the same thing. All right, so that's the definition of the structure. The next thing to do is define a variable that's actually going to be one or more of these students. And this would happen inside a main program or a function or wherever you would normally define a variable. You could do it globally. And so to define a variable that's a type student, we use the following syntax. Struct student, and then the name of the variable. So I'll just call it S1. This is just like saying integer X, character C, character star buffer. In this case, instead of saying integer or character star, I'm saying struct student. So this creates a variable named S1 whose type is struct student, which means S1 contains inside itself all of these pieces. Okay, these things we call fields. So S1 has 3 fields associated with it. So in my program, if I use an S followed by a 1, that refers to the variable, the entire structure, which has all of these pieces. But if I want to access one particular field in here, you put a period, and then the name of the field. So S1.SID refers to this integer field within this particular variable, this struct student. So I could say s1.sid equals 1, 2, 3, 4, 5. And if I had declared a second struct student up here using a comma, I could say s2 student ID equals 67890. And this is a totally independent variable from this. Right? This is part of S2, this is part of S1. They're in completely separate areas of memory. So that's defining a structure, that's declaring a variable, that's accessing the fields of the variable. The other thing we typically want to do is we want to pass these structures around to functions. And again, it works just like passing any other type of variable. Integers, characters, doubles, doesn't matter. So I can make a function, let's call it void subroutine, and I can say it takes an argument which is an integer x, and it takes a second argument which is a struct student, whatever we want to call it, s. And a curly brace, and you can put whatever code you want in here, but at some point, if I say s.gpa, right, that's picking off a field from this struct student. And in my main program, suppose this is my main program up here, I could say something like sub 4 comma s2. And that calls my subroutine, and x is going to be equal to 4, and s is going to be equal to s2. So when I say s.gpa in here, I'm actually referring to s2.gpa, whatever s2's GPA field was. Does that make sense? So you've seen these before, possibly a long time ago, but it's a convenience in some way, kind of like an array is a convenience. Instead of having 5 things that we call 5 different variable names, we use an array, and we can just say array name bracket 0, 1, 2, 3, 4. Same idea here. We could do this by saying student1.name, student1.sid, student2.name, student2.sid, but that's prone to error and wordy and takes more work. And this combines those name, GPA, student ID in this case, into a single thing. Yes?
When you pass a structure to a function, is it by reference or?
It can be either, although we're going to talk in a little bit why everything is always by value. But in this example here, I'm passing the structure itself, right? Typically what we're going to do is we're going to pass the address of it, though. We're going to pass a pointer to it, because we'll want to modify it. Or if we're working with an array of structures. But the snarkier answer is that everything is always passed by value, even if you pass the address of something. But that's another conversation to have probably tomorrow. All right, so the mechanics need to be worked out, right? So you want to write some code and define some structures and give them values like this and retrieve the values and then pass them to subroutines and access the fields within that subroutine and so on. That's practice code, okay, to make sure the mechanics are okay. For now, to access a field, we just use a period. That's going to change in about a week. But for now, just a period gets you a field. And this also starts to look a little like what we're going to be doing in 223 when we start playing with objects in Java. We're going to be working with these kinds of things all the time. And our variables are going to be these large structures, and we're going to pull off fields, usually using a dot. So this is all stuff that you're going to see again and again. So let's take a quick look at ODP 202, which is due tomorrow morning at 8. So you're defining a structure named node that contains 3 fields. Okay, they're all integers. They should be named data, next, and valid. So you can set it up the same way that we just did this example student. But the structure name is node, and the fields are named data, next, and valid. Okay, these ODPs are partially an exercise in being able to follow a specification. If you name your second field next with an uppercase N, when you try to assess, it'll probably give you a 0. Actually, it probably won't even compile. So you really want to follow this to the letter. Okay, so your goal is twofold. 1, define the structure, and then 2, make a function named init. And the prototype for init is down here, so I'll generally give you a prototype for these functions. So init does not return anything, it returns a void, but it accepts a pointer to a struct node. So what's a pointer to an int? It's an array of ints. A pointer to a car is an array of cars. So a pointer to a struct node is an array of struct nodes. All right, so what does init do? It initializes the elements in this array. So element 0 is special. For element 0, you set the 3 fields as shown here. The valid field is 1, the data field is 42, and the next field is -1. For all the other elements, the valid field is 0, the data is 999, and the next is -5 nines. Does that make sense? All right, that's the totality of ODP 202. So define the structure, and then write a void init that takes a struct node pointer. Put a loop inside that sets elements 1 through 99 accordingly, and set element 0 on the line above, and return. Okay, I recommend writing a test program. Write a main program, which also defines the same structure, and create an array of structures. So how do we do that? That's all it takes. Struct node data bracket 100. Now you've got 100 struct node datas. Struct nodes. So if I say data bracket 0, that's a struct node. So I can say data bracket 0 dot valid equals 1. I can say data bracket 99 dot valid equals 0, and so on. So you can keep coming back to the idea of what do you do with other variable types, and try to think of struct node as just its own type of variable. If you remember type defs, you can actually use a type def to create a new variable that's the same thing, a new type that's the same thing as struct node. And then you could have a variable type called myNode, and this would just be myNode data instead of int data car data. And then it really looks like just another variable type. All right, so write a main program, define the structure, make an array of 100 of these struct nodes, call it whatever you like, and then pass it to your init routine. And when you come back from init, start printing out the values of some of the fields. And you should see that they've been initialized the way that the assignment tells you to. If it's not happening, if it's seg faulting, something like that, right, then something's going wrong, possibly in the array declaration, maybe your for loop's going out of bounds. You're at a debugging stage at that point. All right, assuming that you've written your main program, you've tested this, and you believe that it works, now you're ready to send it into the assessment system. So you compile it as usual. Right, so assuming you put your init function in a file called init.c, this is how you build your test bed. gcc-o main, and then temp main.o is the test bed, and init.c is your code. Link them together, and then go ahead and assess it with the assess command, and hopefully you get 100%. If not, then go back to your main program and stare at it and try some different tests. Or run this in the debugger, right? GDB is a good way to dig into this and try to figure it out. And if you're totally stumped and it's just not working and you can't figure it out, shoot me an email, okay? Preferably today instead of midnight, but midnight works sometimes. But this closes at 8 tomorrow morning, so sooner is better. So try this after class and shoot me a note if you're stuck. All right, does that make sense? All right, a couple of general things I want to mention. There's a discussion area of Canvas, which you're welcome and encouraged to take advantage of. With one caveat, which is I would rather people don't post working code there. I figured out the assignment, it was pretty easy, here's my code, right? You don't want to post that because other people see it and you can't unsee something once you've seen it, and so then it's hard to write your own version of it. But it's perfectly fine to say, you know, I'm trying to do this and I'm getting some weird error, and try to isolate a few lines of code where you think the problem is or where it's seg faulting or something. You can go ahead and post that. And more throughout this course, if you email me, I will probably turn it into a discussion section, right? Now, obviously, if you're emailing me about something personal, I can't make it to class, or I'm, you know, have to miss next week or something like that. But if you're sending questions, right? I'm not sure why it keeps seg faulting when I use this particular test case. Chances are I've gotten that email from a few other people as well. And at that point, I'll go ahead and post a discussion, start a discussion in Canvas saying, you know, some people have been having this issue, here's something to think about. Or run the debugger and look at this and see what that tells you about your algorithm. Something like that. But you can always start that yourself in the discussion area. Make sense? It's a good resource, and the reality is, any question that you come up with, probably other people have the same question. And getting some sort of crosstalk going among you students is really, really powerful. Because sometimes I'll explain something 3 different ways and it's still not making sense. And another student will explain it and bingo, suddenly it clicks. So it's a good resource and we want to take advantage of that throughout this course. All right, so let's go back to looking at storing data in something like an array, what we call the linked list. And I'm going to start using the language of structures. Okay, the reason being that programming assignment 1, which is going to be this linked list that we're developing, will require you to use structures. And in fact, what you're doing in ODP 202 will be usable as one piece of PA1. Okay, it's one of the functions that you'll want to write. So if you remember where we were yesterday, we were looking at an array. So we're starting with an array of just 5 numbers, and it's sorted. And we like sorting because eventually it's going to make it faster to search for things. And now we're trying to insert, say, the number 6. So these other spots are unused for now. So we want to insert the number 6. And the traditional way to do this, to keep things sorted, would be to put the 6 right here where the 7 is, and then move everything down. So copy 20 down, copy 12 down, copy 7 down. That frees up this location. Put your 6 there. And that's an expensive operation. It's a lot of memory access. It's going to slow things down. So the idea was, instead of assuming that our data was stored in sorted order, we were going to add a second element to each entry. So now we're going to split up our entry into 2 fields. This is going to be called data, and this is going to be called next, just like your ODP. And next is going to tell us the index of the next number in our sorted list. So 4 is our first number. We're again assuming we always start at 0. But the next number after 4 is the number at index 1. So we put a 1 here, and that gets us to 5. The next number is 7. That's stored at index 2. So we put a 2 here. The number after 7 is 12. That's stored at index 3. The number after 12 is 20, that's stored at 4, and the number after 20 doesn't exist. 20 is the end of the list. And so we're going to put a flag in here. So -1 means end of the list. So we want to insert the 6. Instead of moving things around in memory, we're just going to put it in the next available location. So we'll put our 6 right here. And we're going to adjust some of these next fields. So the 6 should come right after the 5, which means 5, instead of pointing to the 7, should point to where 6 is, which is down here at index 5. So now our ordered list of data starts with 4, goes to 5, goes to 6, and from there, where should it go? It should go to 7, which is stored at index 2, so we set the next field to 2. And we're done. We put our new number in this next location. We change this to point to it, and we change this to point where this used to point. And we've inserted a 6. Very little work. The price we paid for that is that to go through our data, we can't just say 4, 5, 7, 12, 26. We've got to follow these pointers to the next node. We've got to say 4, 5, 6, 7, 12, 20. So it takes a little longer to go through, but order of complexity is the same. It takes an extra operation. So it's a linear slowdown, which we can live with. All right, now suppose we want to insert 10. Well, you and I can look at this and we know exactly where we're going to store this 10. Right? We're going to store it at index 6. But how are we going to tell the computer where to store this? It's got to somehow know that we're using those first 6 locations, and the 7th location, index 6, is free. And remember, in a computer, there's always something here, and here, and here, and here. There's no such thing as an empty space in the computer's memory. There's some value there. And we have no way of knowing if we're looking at an actual part of our list of data or just random junk that happened to be in the memory. So we need a way to differentiate that. And that's where this third field comes in. So we're going to add a field called valid. And valid is just a simple flag. 1 means that this is a part of our set of data, 0 means it's not. So initially, this is what our flags would look like. Those first 6 entries have a valid flag equal to 1. but that entry 6 has a 0 in it, and the entry 7 has a 0 in it. So now we ask the computer to insert the number 10. It's going to start at the beginning, and it's going to look at the valid flag at each location until it finds a 0. As soon as it finds a 0, that's where the 10 is going to go. So that's right in this spot. This is where the 10 goes. Now we got to do 3 things. We've got to take the node that came right before that, which was a 7, and instead of pointing to 3, it's got to point to our new location, which is 6. And this node has to point where that old node was pointing, which was a 3. But we also have to be sure we change the valid flag to a 1. And now this is a bona fide element of this list, this set of data. So how do we initialize an empty list? Set all your valid bits to 0. And that's mostly what your initialize function is doing for ODP202. It treats element 0 specially. We'll talk about why in a little bit. It's something called a Sentinel Node. It's going to make life easier on PA1. But what we're doing basically is we're initializing the valid flags to tell the computer when it first wants to insert a number that it can put it right here in the beginning of the array. All right, still with me? You ready to delete something? Oh, go ahead.
So, when you do insert something new, like the 6 or 10, and you're putting in like where its next value is going to point to that new value.
Mm-hmm.
So, are we having the computer play high loaded there with the next values, or like how is the computer knowing exactly?
Really, the only way is going to be start at the beginning and check each location. But we could start devising some structures to keep track of where all the zeros are. And then any time that we want another location where the valid bit is 0, we could pull that out. And it gets to starting developing something that's called a heap memory, which is really how this works in our operating system. But for us, we're going to do the inefficient but straightforward way, which is just start at the beginning, go through, and find the first 0.
When you stick the 10 in 6 slot, how do you know what next to put it in?
Yeah, like how do you decide, okay, this is, it's pointing at index 2. So how's the computer identifying 2 as the index?
So again, we're going to have to do this the very slow, painful way, which is start at the beginning. We're inserting a 10, and I'm going to talk about this more when we talk about the PA. But as a preview, we're going to start at the beginning, and here's a 4. It points to a 5. It points to a 6. It points to a 7. All of those are less than 10. So we keep going. That pointed to a 12. The 12 is bigger than 10. So right there we know we need to insert the 10 before this. So we've got to remember what the last node was that we found, which was this 7. And then that's where we're going to make our updates. So we're going to change that thing's next to the index of our new piece of data, and we'll make this point where that thing's next was. Yeah, you need to keep track of the previous. And there's all these little details, and like I say, once we start talking about PA1, which we'll do tomorrow, we'll go through this and we'll write out some pseudocode, and we'll get away from this array notation. We'll start using pictures, which will make this a whole lot clearer. All right, other questions? So again, this is for many of us a first exposure to this idea, right? So the details don't necessarily click the first time. In fact, they almost certainly don't click, which is why we're going to have a series of ODPs and PA1, and then PA2, which is 2 weeks down the road, we'll be doing this full blown with memory pointers. And then we're totally off and running on bona fide data structures. All right, so let's do a deletion. Let's delete the number 7. So again, we need to find the 7 first of all, and we're going to do that just by starting at the beginning of the list and marching through until we get to a 7, or we hit the end of the list, in which case there was no 7. So we'll start with 4, that's not a 7. That's followed by index 1 is a 5, that's not a 7. That's followed by index 5 is a 6, that's not a 7. Followed by index 2 is 7, hey, that's a 7. Okay, again, we need to remember the previous node, so we're going to need to remember that this was the node 6 that was pointing to 7. We only really need to make one change here to delete the 7. We'll need to do some housekeeping. But we need to change one thing in here to effectively delete the 7 from our list. Yeah.
I changed what the 6 is pointing to.
Mm-hmm. What do we change it to? Change it to what the 7 is pointing to. So since we're deleting the 7, we're going to take the node right before it and change that to point where 7 was pointing. And that's it. It's deleted.
So, in that case, could we also make a change the value?
Absolutely.
To make that usable?
Absolutely, because if we don't do that, we've got a memory leak. We've got something that's using memory, right? It's taking up a spot in our array, but it's not actually representing any piece of information we care about. So the other thing we have to do is change this to a 0. If you don't do that, it still works, but after you've inserted 100 numbers, you're out of space, if this is an array of 100. So we set that to a 0, that frees that location. So now if we were to insert 15, we're not going to put the 15 down here. The program's going to go through, it's going to look at valid bits starting at the beginning, in use, not in use. Right there is a location in our array that's free for us to use because it's marked as not valid. So we're going to put our data here. There's a 15. We need to find the node right before it, that's a 12. And instead of 12 pointing to 4, it's going to point to whatever our new location is. And this is going to point wherever the thing that came before it was pointing, which was a 4, so this becomes a 4. And then you've got to set the valid bit to a 1, otherwise the next time you insert it's going to overwrite that. Making some sense? Alright, we're going to abandon this for a minute and look at this in pictures. And when you're writing code to do linked lists, PA1, PA2, you're going to need big pieces of paper and a nice fine point pencil and a good eraser. Okay, pictures will help you a lot here because the code's all going to look the same. Okay, it's going to be this thing's equal to that, and that thing's equal to this other thing, and this other thing's set equal to 1. And going through that kind of code and trying to figure out what's going wrong with your program is going to be really frustrating. So what we're going to do is we're going to draw pictures to show us what's supposed to be happening to our variables. And when we write a piece of code that says something, we can make a corresponding change to our picture and see how this changed the layout of our data. And if our program is not working and we do that, eventually we'll find, hey, this thing's not pointing to the right place. And it's a whole lot easier to do that graphically. So, logistical comment. I'm snapshotting these slides, but I'm also recording the lecture. This is experimental. I'm not live streaming it yet. But I'm recording it, and I'll upload that to YouTube, and I'll make a channel for 222 Winter, and you'll be able to find the videos there. I'll put a pointer to it in Canvas. Assuming all of this works, the 215 lecture was about 4 gigabytes, so, and there might be some resolution issues. But we'll nail this down eventually, but at least the snapshots of these things will be posted on Canvas, same as the other days so far. All right, so here's how we can picture this graphically. We're going to picture data and next. I'm not going to worry about the valid bits, because if something's not valid, I'm just not going to show it in my picture. But suppose I have a list of data. Let's just say it's 2, 5, 10, and 12. So here's how I would represent that. So I'm just going to draw arrows. So 2 is a piece of data stored in this node structure, and that node points to another node containing a 5. And that points to another node containing a 10, points to a node containing a 12. And this node is the end of the list. It doesn't point to anything. So I'm just going to write null down here. The way to think of it is there is no pointer from that node. Now we'll code that by storing a next of -1. And if we're doing this with actual pointers, we'll actually set it equal to null, which is a 0. But we'll just think of it sort of logically as it's a null pointer. It's not pointing anywhere. That's the end of the list. All right, so let's insert a 7 into here. We create a new node. We set its data equal to 7. We find the previous node, and instead of pointing to 10, we point to the 7, and the 7 points where that previous node pointed. That's our whole insertion. So that's a little bit easier to grapple with. But what we just did, putting a box, putting a data value in there, changing one pointer, changing another pointer, right, that corresponds to, in the case of the array of structures, changing those actual values, right, copying this into the next free location, changing the next field on the previous, setting the next field on this, and so on.
Is there any like predefined C linked list function, or do you just make a structure?
You can definitely find linked list libraries and such, but the C language itself, no, and if you find something, I don't want you to use it, right? So our goal is to do this from the ground up. In 2.23 in Java, we'll start using some of the existing classes that implement things like this, so that we can use these and build on top of that. All right, so now how do we delete? Let's delete the 10. Well, we find the node before, which was a 7, and we change it so that instead of pointing to the 10, it points to whatever 10 was pointing to, which is the 12. And we just deleted the 10. So now if we decide we want to see what all the data is in our list in sorted order, the first number is 2, that's followed by a 5, that's followed by a 7, that's followed by a 12, that's the end of our data. Pretty simple, other than a few million details. The concept should make sense. The implementation, whole different issue. Okay. At this point, right now, my main concern is, does the concept click? Okay. If you don't understand this, there's no point in writing code. And I've seen students write code trying to implement their program, and I'll ask them, okay, show me with pictures what this piece of code is supposed to do, and they're like, I don't understand the pictures, I was just writing code. Okay? You gotta understand what your program is supposed to do before you can try to write code to make that happen. So this is how I want you thinking about linked lists for now. Think of pictures or whatever version of this makes sense to you. It could be numbers, it could be something totally non-visual, but something that lets you think in abstract terms about here's a list of data where each piece of data points to the next thing. That's the essence of a linked list. And once you've got a way to sort of represent that on paper, then you can start thinking about code. And how am I going to write some code to actually do what we just did here, where we find this node and we remove this and we change that pointer to point over there. The pictures will be good. If there's no questions, we're going to go on to something a little weird. This is slightly difficult to motivate in the context of making an array into a linked list, but it will work better when we get to PA2. But for now, you just kind of have to go on faith that there's a good reason why we're doing this. So let's look at our linked list. So there's a list of 3 things. We need a way to get to the beginning of the list. Everything that we do starts with the first node, and we move down by following what each node is pointing to. But we've still got to have something that gets us to this first node. Now, in the case of an array, it's just going to be use element 0. That's going to be the first node in our list. But when we start putting this into memory, and these are actually pointers to locations in memory, what happens if we delete the number 2? If we delete this first node, it basically goes away. And when we say, okay, let's start with our list, we're going to look at something that's not actually a part of our list. We need to somehow change this to point somewhere different. In the language of our array, we no longer automatically start with index 0. We might need to start with index 1. Or we might need to start with index 5, depending on how jumbled up this array became. So if we delete the first node of our list, it's kind of an edge case. We need to do something different and point somewhere else. If we delete the 5 and we delete the 10, whatever this is that's pointing to our list, where is it going to point now? Because there's no data in our list. Maybe. So it could point to a special value like -1, which we know is not a valid index. But now, every time that we write our code, we've got 2 cases to deal with. If our list is empty, right, if our thing is pointing to -1, we have to do one thing. If it's not empty, we have to do something different. Right? Normally, we're just going to take what it points to and start searching for our value, for example. But if it's a -1, we need to do something different. So we're constantly going to be coding a pair of cases. Why? Because nothing is somehow very different from something. Right? When we're writing code, if we think we have something and we actually have nothing, we usually end up with a seg fault. So we get lots of special cases. So we're going to use a trick. And the trick is going to be to use what's called a Sentinel node. And like I say, at this point you can take it on faith that there's a reason to use a Sentinel. It's certainly not going to do any harm. But if it's not clear why this is helpful, just kind of run with it, and as we move towards PA2, it'll start to be more obvious, and we can talk about this in that context also. So here's what a Sentinel is. It's a dummy node. It's a node where we don't care what the value is. The only purpose the Sentinel has is to point to the first node of the list. So an empty list looks like this. So here's my list, and it points here, and this is an empty list. A list which has multiple values, same Sentinel, same data, but it looks like this. But now, if I want to delete the 2, it's exactly the same algorithm as any other number that I want to delete. Find the node before it and change it to point to whatever 2 was pointing to.
So you said that we don't really care what the data is inside of the Sentinel node. So how do we prevent somebody from deleting the data that could be inside?
Don't ever consider the Sentinel when you're looking for the number to delete. So everything that we do with the list, we're always going to start with this first node, whatever it points to.
Yeah.
So we're never going to actually look at that data. Now in your init program, I ask you to set element 0's data value to 42. This is because element 0 is a Sentinel. And if you print out your data and you see a 42 that you didn't put in there, you know you're looking at the Sentinel. And I'll try to delete the number 42 without storing it. And if it tells me it's succeeded, I know it's deleting the Sentinel if it's not supposed to. So you can put a number in there that you know the value of as a safeguard. But now deletion is exactly the same for the first node as any other node. And inserting something before the first node is exactly the same algorithm. And deleting all of your nodes, there's no special cases. Because our list is empty, but we have at least one node in all cases. That's the Sentinel. All right, so that's all the prequel that we need to talk fully about PA1 tomorrow. So we'll go through the assignment. It's already been posted on Canvas, so you can read through it on your own. You can start thinking about the interface part, which is a 224 type program. But we'll start talking about the code involved with actually doing the structure tomorrow.